Modern microwave devices, for example amplifiers, oscillators, synthesizers and active mixers, many times can be directly connected to 5 volts power supplies, and the USB standard many times can be a convenient source of power because they are everywhere, especially on your workbench. As examples, we have these devices here, the ADL 58016 GHz active mixer, this amplifier based on the Gali 39 7 GHz amplifier, these other ones based on the AVA 183A amplifiers, and so on. The problem is that the power supply can impact dramatically the phase noise performance of those devices and also of the setup used to measure the phase noise. In this video I show how I measure the noise of power supplies, especially those derived from the USB standard, using a 6 dB low noise voltage amplifier. I borrowed this design from the FES channel, links below, and I changed the original design very little, basically replacing the amplifier itself for a lower noise one, the TTHS 4032 from Texas Instruments. And here is the interior of the amplifier, and as I said before, a copy of the one presented in the FES channel. And here is the frequency response of the amplifier, 5 Hz to 100 kHz. Let me zoom in. Unfortunately, with this oscilloscope I can't go below 10 Hz, but you can clearly see that the maximum frequency is about 100 kHz. The first thing to do is to measure the intrinsic RMS noise of the amplifier. In this case, the input is grounded. We can see here that it's about 1.7 millivolts RMS. This is what we just did. Now let's measure these power supplies here based on the Texas Instruments TPS 73801 low noise regulator. I have included a 50 ohms load inside the amplifier, so to measure the noise with 100 milliamps current. And we have here, let me zoom in, 114.4 millivolts RMS. And here is how we calculate the measured power, and the result is 114.4 microvolts RMS. In this case, the amplifier intrinsic noise can be neglected. We have to measure this way because it's uncorrelated random noise. The noise is specified in the datasheet of the regulator is 45 microvolts RMS in the 10 Hz to 100 kHz range, considering 100 milliamperes load. Now I have another set of power supplies based on the MAX 38904B regulator which has a declared noise of only 5.1 microvolts RMS from 10 Hz to 100 kHz, or 9 times less than the TPS 73801 regulator we saw before. The problem is that the latter can accept voltages at the input up to 20 volts DC, and the MAX 38904B will accept only up to 6 volts DC. So it's fed firstly by a low noise linear power supply. But it's important to know that this regulator has a PSRR, power supply rejection ratio, of about 60 dB. So theoretically, the 5.5 volts power supply noise is being attenuated by a factor of 1000. And we can see here, after zooming in, that the measured noise is 38.07 microvolts RMS. Now I replaced the linear power supply by 4 AA batteries in series, and we can see that the noise measured at the scope is 6.7 millivolts RMS. If you consider and discount the noise of the amplifier, we will have about 6.4, 6.5 microvolts RMS. Now let's measure the RMS noise of the set of 4 AA batteries without any regulator in between. Let's see what's we have here 9.1 millivolts RMS. In this case, we will have to consider the amplifier noise, 1.7 millivolts RMS, and then we will have here 8.9 microvolts RMS for the batteries. I will now measure the quality of some USB sources I have here on my workbench. And for that, I won't use the amplifier. As you will see, the noise level are so high that would saturate this amplifier. To have a fair comparison, I made this second order RC 100 kHz filter here. Let me show the response of the filter. I will measure my laptop, the oscilloscope I'm using, this Rhodes-Schwarz spectrum analyzer, this Keysight frequency counter, and this Siglent waveform generator. The 50 ohms load is right here at the oscilloscope input, so the USB power supplies will be supplying 100 milliamps. Let's start with my laptop. Let me 10.8 millivolts RMS. We can also see here deterministic noise, about 42 kilohertz. Now the oscilloscope about 800 microvolts RMS. Now the brochures. One 1.7 millivolts RMS. Well, now you're gonna measure the key site and signaling, but for that I have to use the amplifier. One 165 microvolts RMS, considering the amplifier. And finally, the signaling. Here we set the statistics. Seven 742 microvolts RMS. There is also apparently something else here. 46 kilohertz. And here is the summary of the measurements. Well, that's all I had. Thanks for watching.